So, and then you wrote it nicely. You said 2, and then you moved it to the bottom, right? I always like the first time you see that, I like to keep going with that.
So this is like a harmonic motion.
Yep.
Huh.
That's exactly it. I think you're going to see a pattern to this. What's the next one?
So
negative 3 times 2 is negative.
Negative 3 over x4.
What's that? Negative 6? And then this goes to a negative what?
Minus 4.
I'll write it again. I'll box all these. I think you can see a pattern to this thing. First of all, the signs keep alternating. Do you see that?
Uh-huh.
Negative, positive, negative, positive. That was a 1, that was a 2, that was a 6. Let's do one more. 1, 2, 3, 4.
So 24.
Positive,
Yep.
x to the negative
5. So basically, whatever you have to square it basically on the numerator.
Yep. And if you're curious, is there a pattern in this thing? Can you see it?
You're multiplying the exponent times the number in front of x and then taking the exponent and moving it down.
That's 2. That was 2 times 3. How do we get this number? 2 times 3 times what? 4. So you see that?
Mhm.
Yeah, I got 2. 2 times 3. 2 times 3 times 4. And anybody in this class have any experience with factorials? That's what it's doing. These are factorials. That's 4 times 3 times 2 times 1. That's 3 times 2 times 1. That's 2 times 1. And you go, oh, you could predict y. I bet you get in your, that'd be a good bonus. That'd be a good, you go, what's y to like, what's the 1,000th derivative? No, the calculus don't go that. And when the TID4s, they blow up after you do like 69 factorial. The thing won't even do 70 factorial on the calculator. Anybody know where the factorial button is? Do you want to look at it real quick? Try 70 math PRV and look for a factorial symbol and hit it. And hit enter and tell me what your calculator says. And then afterward, I'd like you to try 69 factorial and tell me what it does. First, try 70 factorial. It'll lock up on you. Well, it'll lock up. It'll just tell you some goofy message.
Overflow.
Overflow. Too big for this tool. Because that's 70 times 69 times 68 times 67 times 66 times. It's huge. 69 factorial will calculate. All right, how big is it?
1.7 times 10 to the 90.
And then way at the end of that 1 point,
98.
blah, 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 blah. Look at this thing. Right? So if I said I'm going to do a bonus, I better not do something to this. I'd have to do like, give me the 69th derivative. You can finally see the pattern to it, right? Know what the factorial is? See, that's a 4 factorial. That's 4 times 3 times 2 times 1. That's 3 times. It'd be that factorial. That factorial divided by x to the, you'd have to go higher, right? Wouldn't that be a good one? And what's the 70th derivative? No, we can't do that. 69th derivative. It looks like it would be 69 factorial over x to the what power?
70.
That is a good bonus. Right?
Mm-hmm.
I don't have the time to do 70 derivatives. But you could actually put that number in right up there. Great job!
Could you explain that again?
Oh, you want to see that?
Yeah.
You bet. Did you see? Oh, I just erased all the answers. Did you see those numbers that were coming up in the top? It was like 6, 2 times 3. And the next one was 24, which is 4 times 3 times 2 times 1. And so they call those factorials. And a factorial is just the number multiplied by all the numbers downward, keep getting to 1. So 5 factorial math is 5 times 4 times 3 times 2 times 1. But did you see this pattern? Like this thing had the 4 times 3 times 2 times 1, but it had a 4th derivative. But it was x to the negative 5th. And you see the pattern, you go, all right, so then you could jump to like something way down the list, the 69th derivative. Right? What's the 69th derivative of that? We're like, well, then this would be the what? The 69 factorial. That's the factorial symbol, that exclamation point. But then it would be over, notice it was 1 more than that. You see that? 5, 4, 4.
That only work with y equals 1 over x.
There you go. Not every function has a nice pattern like this, but some have some neat symmetry to it, or neat patterns to it. Cool. When do you do a lot of factorials? Calc 2. Who's going to Calc 2? Yeah, you get a lot of factorials. You get used to them. If you're like, oh, that's weird. You're like, a lot of factorials. All right. So, who's got a textbook? Don't worry if you don't have your textbook with you. Let's look at some, like, which one looks weird? I'll pick the first one. Before we do these, let's look at, like, oh, we got power rule down, don't we? And I hit the two major cases, the 1 over x and the square root of x. But is there anything else that's weird? Well, I'm going to start with the first one. It's number 23. And then you can scan it over and go, oh, that one looks weird. And I'll tell you if it's bogus or if it's a good one. Like, if it's lame, I'll be like, 23 is good, though. What do they have? Find the derivative. Or they say differentiate. And when if that's the verb, the directions say differentiate, they want you to get the derivative. So they go differentiate. They really should say, though, differentiate y with respect to x. They should say. Because here's y, and it's in relative to x. Coming down the road, everyone, in the next half hour or so probably, we'll be getting into something called quotient rule. Well, yes, you could use the quotient rule. It's for fractions. I just wanted to show you, if there's only one element in the denominator, you don't need quotient rule. One element, not like a binomial. So again, quotient rule, when you got binomials in the denominator, something like that, quotient rule. But if it's just one solo thing, did you know you can split up fractions? Look at this. Can't you think of this like this? Look. And you can just power rule all three of them, if you don't mind. You can do that in math. Power rule the first, power rule the second, but before you do power rule, you need everything upstairs. So let's take this slowly. Some of you do like 2-3 steps in your head. Pretty cool. Really good at algebra. You come and you're like, ouch, I know what that is. But let's take this slowly. What's that power in the denominator?
X 3 halves. Oh.
Oh, right. That's good, Art. So you're hitting all of it right in his head. That's x to a 1/2, 3 over. Well, that's what it means, right? Can you get those upstairs?
Yep.
How do you do this in math? And you'll make sense of it.
So
You do what with these? I heard you subtract powers. Okay. Well, let's subtract powers. 2 minus 1/2? 3 halves. That's a 1. What's 1 minus 1/2?
half.
See, no more fractions. Now be careful, when that's x to a 0. So x to a 0 minus x to 1/2, you get 3x to the...
Minus half.
Cool. There's only one danger of this. Sometimes you did so much algebra, you think you're done the problem. Good, move on to the next one. You're like, whoops, I never differentiated. Right. Wait a minute, I just manipulated. I never what? Took the derivative. So what's this derivative? I got it from off here, right? What's y prime now? All right. Do the 3 halves thing in front. 3 halves in front. Take 3 halves, subtract 1.
Minus half.
Good. 4 times 1/2 is
2.
2.
X minus half.
Good. 1/2. Subtract 1. Make 1/2. And lastly,
That should be
way at the end, negative 1/2 times 3.
negative 3 half. Yep.
And then you just You can leave it like that one, unless you want to change those negative exponents. Here, I'll put an or. Or. You can do a square root there. You can do a square root there. Oops, it's a minus. Put that down there. Now, everyone, if the textbook on that problem did factoring, there's no need to do that. Would you remember that? I'd be upset. Someone in here thought you had to do some kind of factoring. Or
Professor.
factor something out.
You forgot the 2 on the last one, 3 halves.
3 halves on that last one.
All the
Thank
way.
you so much.
Uh-huh.
All right, thank you so much.
No problem.
But don't think should I factor out something? Nah, I was a problem to make sure you knew that you could actually do the power rule there. Now, did anybody spot any goofy ones in there? I'll look for one. I found one. Yeah, I don't like to put this one on the test, because it might get some. Differentiate. Hey, if you know this one,
Mm-hmm.
don't shout it out. Give everyone a little time to think about that. Differentiate. Put it in yellow. The problem said differentiate. Get y prime. Who knows the real answer? What is it?
0.
0. Did anybody do 5 in front, e to the 4th? Hold up. Is e a variable? E is like pi. E is a what?
Constant.
Constant. That's a constant. That's just a number. They threw it in there. So that's not 5 e to the 4th. What's the answer?
0.
It's a number. Not out to trick anybody, right? But they slip that in there all the time to make you go, don't forget, e's not a variable. Differentiate what? It's a constant, 0. Slope 0. It's a flat line, y equals e to the 5th, it's flat. I don't see any other ones. I looked for the fraction. And we did equation of a tangent line to the curve already. That's my only concern. And when we did one of those, we did that with the square root problem, right? Cool. Experts at power rule. You know how to do square root of x, you know how to do 1 over x. You know how to do if it's a goofy fraction like this. You break it up. Got it. You got it. Now, by the way, on that note, I know it had an E. Might as well hit it now. There was an E in that last one, there was 0, but there's one derivative. There's one special derivative where its rate of change, everyone, is the same as the original expression. So never do power rule on e to the x. And you go, why? Power rules for these monomials, x squared, right? Never do power rule on this. I've seen it before there, everyone. Cross this out. People go, oh, all right. Look at this stuff. Right? No. This one's special. I mean, can you believe this? The rate of change of e dx, it changes, it's proportional. So derivative e dx is just
e to the power x.
e dx.
Actually, on 2.8 there was a graph.
Is that really?
Yep. Where you have to, in that way you
It
get
shows the slope, right?
Yep.
And this graph grows so fast. So its slope is changing so fast. The slope. And the derivative is e dx. So what's the second derivative?
Same.
To that x.
What's the 1,000th derivative?
Same.
I'll put 1,000 e dx. Cool. Hey, let's talk about the constant rule. I don't write the constant rule. It's written in the book. Constant rule means, you've already applied it. What if there's a constant in front of these things? What if there's just a constant in front of them? No effect. Right? Don't you agree?
Yep.
Constant rule. We were applying it before. When I had a y equals 10x squared, and you did the power rule, you just left that constant there, didn't you? Constant rule. We don't have to write on the board. Constants in front, you can always let them sit out in front of the derivative and let them get multiplied by things. Well, if e to the x, e to the x, e to the x, well, 5 e to the x becomes 5 e to the x becomes 5 e to the x. Cool. Right? So that's special. I'll erase all these. This will come up later, but we might as well talk about it now. These are special functions, right? They call them the transcendental functions and stuff. You ever heard of that? Ooh, the natural log of x. The natural log of x. We can prove it too. If anybody's curious later on, you go, how do I know this is this? I won't do it now. Now, if you're curious, here's its derivative. 1 over x. Cool. Yeah, I'm gonna leave a note. If you're like, a lot of you are, which is awesome. You get very curious, mathematically curious. And you're like, great, thanks, professor. You just told me the answer, but you're very curious a lot. I promise you, I'll show you why. But to do it, we need another skill. We need something called logarithmic differentiation. And it comes up later in this section. I think it's like 3.5. I think they introduced that in section 3.5. So when we get to that, I'll explain why the derivative of natural log of x turns into 1 over x. Like you can do a math proof to prove it.
Professor,
That's its rate of change.
what if you do like a graph in that way? You can also show it like the way in 2.8, like you can do the like slope like that.
It's a great idea. I mean, it's good to know what the graph of e to the x looks like and the graph of natural log of x looks like. It's always good to know these two graphs. Well, there's e to the x. Exponential growth. What's the graph of y equal n of x look like? It's the inverse of that function. So a natural log of x does this. But it's almost like if you could look at this slope here,